This model has been designed to show how the cochlea works, as well as reveal some of its mysteries, in addition to explain the operation of the cochlear implant. On that very subject, in my humble opinion, it's probably inappropriate to call it cochlear implant because after the surgery, the implant remains intact. To be more precise, I believe it should be referred to as a cochlear electrode implant because that's precisely what has been implanted into the cochlea. Starting on the left, we have an electrode input, which is a series of pulses to represent an audio signal, which I will turn on now. So the LEDs you see flashing there represent an audio input going to the cochlea. This model that you see now is actually the uncoiled version of the trapezoidal cochlea. On the front, you'll see that's the scala vestibuli, shaped like a trapezium. At the very end there is the oval hole. And down below here is the scala tympani. We notice in the LEDs on the left, they're all scrunched together and spaced out on the right. And that's because the high frequencies occur on the left and of a logarithmic scale, so they tend to squeeze on the left and expand towards the right. On the upper portion, I've made 3 partial cochlear models. You can see there. So starting on the left, this is what a normal cochlea would look like, whereby the hair cells are still functioning on the inside of the cochlea and the information is transferred to the brain via synapses. In the case of the cochlear implant, an electrode is inserted into the cochlea, especially the scala tympani, and there are 2 possibilities of alignment. So if I just show by a light, this is known as the perimodular electrode, and it tends to cling to the inside of the cochlea. And the alternative is the lateral that clings on the outer wall. Now, each one of these has pros and cons in terms of the feature, sensitivity, sound quality, frequency response. Now, what is interesting is that, just to recap, in a normal cochlear operation, the hair cells and the ganglion neuron synapse. But in the case of the implant, they do not synapse. Instead, they use an electric field. So I'll show you how now what the electric field consists of. Now, if you can see that needle changing direction, so the electrode sends a signal that changes its polarity, positive, negative, positive, negative, and this in turn excites the nodes of Ranier, which then generate an action potential. So there's no synapse involved in this, strictly using an electric field. That's the first part. And the second interesting aspect is that the signal that drives the electrodes are biphasic. That means they change positive and negative. This is to avoid the contacts rusting, having electrolysis effect, and also contaminating the fluid in the cochlea. So again, it changed polarity, positive to negative. Notice it doesn't go to 0, it goes positive, negative, complete polarity reversals. And once that happens, the nodes of Ranier pick the electric fields up and they generate the action potentials. Now in blue, you'll see now, so that's the action potential that's been generated. And prior to that, we have the synapses. And here's the synapse for the thing. An unusual phenomena or condition is when a tumor grows in the cochlea, and that's referred to as the acoustic neuroma. The neuroma grows very slowly and often takes many years to increase in diameter. So I'm trying to illustrate what the consequences of acoustic neuroma that grows in the cochlea. So here's a model of the acoustic neuroma. And as I move, that illustrate is getting bigger in diameter. So when it's not touching the auditory nerve, you don't feel any impact in that. But as it grows bigger, so I'm going to slide this now, and once it touches the auditory nerve, you notice the speed of the action potential has slowed down. So again, if I remove the acoustic neuroma, it's back to normal. And when it grows big and it touches the auditory nerve, so therefore hearing is impaired, or there's a drastic reduction in the hearing ability.